March 1979. American listening posts detect something deep beneath the Barents Sea, and it's moving at speeds that should be impossible. Faster than anything they've tracked before. It's not only faster than any submarine, it's fast enough to outrun their torpedoes. The Soviet Union has built something unstoppable, and it's caught everyone by surprise. A generational leap forward in material science, nuclear engineering, and computer automation. But this new superweapon will end up being more than the Soviets bargained for. In the late 1950s, the Cold War intensified as the United States and Soviet Union raced to gain the upper hand beneath the oceans. The Soviet Union's strategy was simple: build as many submarines as possible. Attack, guided, and ballistic missile subs poured out of Soviet shipyards. By the mid-1960s, the Soviets would have more than twice as many submarines as the United States. But the numbers weren't telling the real story. Below the surface, American crews could stalk Soviet subs for hours, even days, without ever being detected. For Soviet crews, it was the opposite. American submarines had seemingly vanished from the oceans. Over the previous decade, U.S. naval engineers had developed sophisticated stealth technologies like dampeners, precision gearing, and advanced propulsion that made their submarines much quieter. By comparison, Soviet technology had fallen behind. Machinery sent vibrations through their hulls, reduction gears rattled with noise, and propellers, cast with less precision, shredded through the water. Soviet military planners faced a chilling reality. If war ever broke out, the Americans could find and destroy Soviet submarines before they had a chance to strike back. The Soviets understood the problem. When it came to stealth, they were at least a decade behind the Americans. Simpler design and construction had allowed them to build submarines faster. But now, quantity over quality looked like a mistake. So what do you do when you're caught in a fight you can't win? You change the rules. In 1960, work began on a radical new submarine, built not around stealth, but raw performance. The first objective was sheer speed, at least a third faster than any American submarine. Next, maneuverability. American submarines needed 2 to 3 minutes to execute a 180-degree turn. Soviet engineers would aim for 40 seconds. Finally, raw acceleration. From a dead stop to full speed in under a minute. A burst of velocity so extreme it would overwhelm tracking systems, allowing Soviet crews to close in at blistering speeds, strike with overwhelming force, and escape before the enemy could react. It was an asymmetrical response, a submarine that would make stealth obsolete. What Soviet designers came up with wasn't just a faster submarine. It was a complete rethink of how they operate. At its heart was a revolutionary liquid metal-cooled reactor, delivering up to 3 times more power, allowing the sub to accelerate from a dead stop to over 40 knots in just over a minute, a remarkable feat. But the new reactor came with one critical trade-off. It could never really be switched off. Even when idle or docked in port, its coolant would always have to be kept above 125 degrees Celsius, or it would solidify instantly and permanently destroy itself. But raw power was only part of the solution. The sub would also need to slice through the water, so engineers employed a radical teardrop shape with every inch smoothed over. Even the bow planes would be fully retractable at speed. To cut drag even further, the sub was made as compact as possible. But that meant having to operate with a crew barely a third the size of a typical attack sub. The solution was unprecedented automation. For the first time, computers would manage propulsion, ballast systems would adjust themselves, and torpedoes would load automatically. Navigation, sonar, and target acquisition would all be integrated into one central command system. And the entire pressure hull would be built out of titanium, 40% lighter than steel and far stronger pound for pound, It would allow the sub to dive deeper and survive depth charges that would crush conventional steel. What would emerge was a machine decades ahead of its time, built to outrun, outdive, and outmaneuver its rivals. But only if it all came together perfectly. The first hint that the Soviets were up to something came from intelligence sources reporting that new submarines were leaving assembly sheds at the Leningrad shipyard. But their hulls looked wrong. Ordinary steel, like the kind used to build American submarines, darkens almost immediately when exposed to the elements. These were highly reflective. Analysts suspected titanium, but it seemed impossible. Titanium was difficult to work with. Outside of high-end aerospace programs where weight and heat resistance mattered, it was only ever used sparingly. An entire submarine would require fabrication methods never attempted at scale. Massive hull sections would have to be assembled inside giant argon-filled chambers, hermetically sealed environments. To many, the thought of a dirty Soviet shipyard with welders fumbling around in spacesuits seemed comical. But if the Soviets were using titanium, the implications were staggering. A sub with a lighter and stronger hull would move faster, dive deeper, and survive pressures that would crush conventional steel. Analysts estimated diving depths of up to 1,000 meters, wildly beyond anything else in existence. NATO's anti-submarine arsenal could become obsolete overnight. The West scrambled to respond, fast-tracking the development of deeper diving weapons, new acoustic tracking systems, and faster torpedoes. For the first time in years, the West was playing catch-up. In 1972, the most sophisticated submarine the Soviet Union had ever built left its port on the Barents Sea. It had taken 11 years to develop, but it would lay the groundwork for the next generation of submarines. After years of playing catch-up, the Soviet Union had finally overtaken the West. Then, its liquid metal reactor solidified into one solid piece of metal. A fault in the steam generator had gone unnoticed, causing a leak and the liquid metal coolant to drop below 125 degrees Celsius. The reactor, the heart of the machine, was destroyed instantly. In the blink of an eye, the crown jewel of Soviet naval engineering had transformed into titanium scrap. It was a disaster on every level, technical, financial, and political, and the pressure to cancel the entire program was intense. But with so much already invested, development would push on. The destroyed sub was cut in half. The forward section was sent to Leningrad to serve as a dryland trainer, while the stern, with its frozen reactor, would remain in Severodvinsk. The running joke was that the Soviet Union now had the world's longest submarine. It would take another 5 years before a replacement could be built. The Soviet Union's most daring submarine program had been troubled from the beginning. Initiated in the late 1950s as Project 705 and what NATO would later call the Alpha class, design work dragged on for 8 full years before construction of the first submarine could begin. Once complete, the first sub was meant to undergo extensive testing, clearing the way for mass production. But that's not what happened. Instead, Soviet leadership, panicked by increasingly stealthy American submarines, ordered the immediate construction of additional Alpha subs before the first one was even finished. Pushing an unproven design into serial production without even testing it was a huge mistake. From the start, the subs were riddled with technical problems. Automated systems failed regularly, overwhelming crews. Specialized port facilities, with equipment to keep the liquid metal reactors continually above 125 degrees, were either never built or proved even more unreliable than the submarines themselves. It meant crews had to remain on board to keep the reactors continuously running. This constant operation, never envisioned by designers, made critical maintenance almost impossible. Engineers had planned for cruise and ballistic missile variants, designs that might have seriously threatened American carrier groups, but the endless cascade of technical setbacks kept them on the drawing board. By 1978, after a decade of setbacks and one catastrophic failure, the Alpha was finally ready. 6 more submarines entered service with the Soviet Navy. Not the 30 originally planned, but these were 6 of the most advanced attack submarines the world had ever seen. And they were kept on high alert at Soviet bases, ready to defend the Soviet Union's Arctic bastion. American commanders who encountered Alphas described the experience as visceral. They could outmaneuver and change position at breakneck speeds, dive deeper than any weapon could reach, and accelerate like nothing else in the ocean. But that speed came at a price. At 40 knots, the cavitating propeller and rushing water created so much acoustic interference that the Alpha's own sonar went blind. The submarine wasn't hunting, he was screaming, and the reactor that could never really be shut down turned into a maintenance nightmare. It meant that the subs spent more time in repair than out on patrol. Each Alpha had cost twice as much as a conventional nuclear submarine. And the program also forced the Soviets to develop an entire titanium industry, new fabrication methods, and push nuclear thermodynamics to its breaking point. All for just 7 submarines that barely worked. The scale of the failure was staggering, until you learned the truth. The Soviets weren't trying to build a better submarine. They were trying to invent an underwater fighter jet. Because translated records from its designers revealed that the submarine the world saw wasn't the submarine the Soviets were supposed to build. The Alpha was just the first piece of something much bigger, a revolution in naval warfare that almost happened, one that could have jeopardized the US Navy's surface fleet and even its aircraft carriers. In my new series called Unsealed, I explore what the history books left out and uncover the deeper stories behind machines and what could have been. And you can watch the very first episode right now on Nebula. Nebula is where you can watch hours of exclusive Mustard videos you won't find anywhere else, and my most ambitious projects ever, like my latest feature on Operation Bolo, which uncovers one of the most incredible combat operations of the Vietnam War, where F-4 Phantom pilots turned the air war on its head by dragging North Vietnam's elite MiG-21s into a deadly ambush. You might know the history, but you've probably never seen the battle like this. On Nebula, I'm able to go beyond what's possible on YouTube, with longer runtimes, deeper dives, and the freedom to build something truly cinematic without compromise. And it's where I explore captivating stories behind engineering marvels, iconic machines, and groundbreaking ideas that were supposed to reshape the future. When you sign up, you're not just getting more videos, you're directly funding the kind of ambitious, high-effort projects that otherwise could never have been made. Whether it's Real Engineering's Battle of Britain series, Neo's Underexposure, or Real Life Lore's Mad Kings, we're so sure you'll love Nebula, we're now offering a free 3-day trial, so you can explore Nebula's enormous catalog of high-quality content and see for yourself. To start your free trial, use the link below, scan the QR code on screen, or go to nebula.tv/mustard. If you use my link, you'll also get Nebula for 50% off. That's just $2.50 a month, or $30 for an entire year.